Far from the inner planets and far beyond the orbit of Neptune, the outer region of the solar system extends into space that is cold, sparse, and faintly bound to the Sun. In this region, at distances of many thousands to tens of thousands of astronomical units, the Sun's gravity still holds small bodies in orbit, but light and heat from the central star arrive as only a weak glow. The distribution of icy objects here is not a flat disk like the plane of the planets, but a roughly spherical cloud surrounding the solar system on all sides. This region is known as the Oort cloud in current scientific usage, and it provides a natural reservoir for the long-period comets that occasionally appear in the inner system. Even though no telescope yet resolves this cloud directly, its existence is supported by the observed orbits of comets that must have started from far beyond the planetary zone. Within this outer reservoir, individual bodies are separated by very large distances. Each one is a small nucleus of ice and rock, perhaps a few kilometers across, held in a distant elongated orbit around the Sun. The number of such nuclei is thought to be very large, possibly trillions, but the total mass remains small compared with that of the planets. The temperature in this region stays only a few tens of degrees above absolute zero. Under such conditions, water carbon dioxide, carbon monoxide, and many other volatile substances remain frozen in solid form over billions of years. Energy input from the Sun is so low that surfaces change only slowly, mainly through the steady impact of high-energy particles and the occasional collision with very small debris. The Oort cloud forms early in solar system history. When the giant planets grow in the protoplanetary disk, their gravity scatters many icy planetesimals from the region near their orbits. Some bodies are ejected completely, leaving the Sun and entering interstellar space. Others are thrown into very distant but still bound paths. Over time, the gravity of passing stars and the tidal field of the Milky Way galaxy alter these distant orbits, turning an initially disk-like distribution into an approximately spherical one. The result is a cloud of small icy bodies surrounding the Sun at distances far beyond those of the known planets. This picture is supported by models of planetary formation and by the distribution of observed comet orbits which cluster around energies consistent with origin in a distant, nearly isotropic reservoir. In the outer parts of the cloud, where the Sun's pull is weakest, the gravitational influence of the galaxy becomes more important. The combined effect of the overall galactic field and individual passing stars slowly modifies the orbits of the stored bodies. These changes occur on timescales of many millions of years. Orbits tilt, stretch, and rotate in space, but the bodies remain cold and mostly inactive. The motions are slow, and each nucleus completes only a small number of circuits around the Sun over the entire age of the solar system. In this regime, the Oort cloud behaves as a long-lived archive of primordial material, preserving a mixture of ices and dust that reflects conditions in the early protoplanetary disk. A typical nucleus in this region is dark at visible wavelengths. Its surface is likely coated by complex organic compounds produced when radiation acts on simple ices over very long times. These compounds absorb most of the sunlight that reaches them. The albedo or reflectivity of such surfaces can be very low, making the bodies effectively invisible at the extreme distances where they reside. The only light they reflect is weak and spread out, and they are too small to subtend any appreciable angle on the sky when observed from the inner system. Detecting such objects directly would require instruments of sensitivity far beyond present practice. Compositional diversity within the cloud is expected. Some nuclei may be richer in carbon-bearing compounds, others in water ice or more refractory dust, reflecting differences in where and how they formed in the early disk. These variations in makeup and structure influence how each body responds to heating under different conditions. But while it resides in the outer cloud, those differences remain hidden beneath the same low temperatures and the same dark radiation-processed surface layers. In this way, the reservoir stores a range of materials in a state that changes only slowly with time. Gas activity in the Oort cloud is minimal. At such low temperatures and such weak radiation levels, even the most volatile substances sublimate only at negligible rates. Any gas that leaves the surface quickly disperses into the surrounding vacuum, and is not replaced in significant amounts. The lack of sustained outgassing means that typical cometary features such as commi and tails do not form in this region. The nuclei remain bare and inert with their volatile content locked beneath the surface. Rare impacts with micrometeoroids may excavate small patches of fresher material, but the overall structure remains stable. The density of material in the cloud is extremely low. On average, the volume occupied by each nucleus is enormous compared with the size of the body itself. This low number density implies that collisions between nuclei are rare events. Over the full age of the solar system, most bodies in the Oort cloud never experience a direct impact with another large object. Instead, their evolution is governed primarily by distant gravitational influences rather than by local collisions. In this way, the cloud maintains its population of ancient bodies with only gradual losses to ejection or inward scattering. Despite being dynamically cold in terms of internal motion, the Oort cloud remains sensitive to small external disturbances. The passage of a star within a few light years of the Sun, or the steady pull of the galactic tide over many millions of years, can alter the shapes and orientations of orbits enough to change how close their perihelia come to the Sun. Some bodies experience shifts that bring their closest approach still far beyond the planets. Others undergo larger changes that move them into paths that reach different distances from the central regions. From the point of view of the outer reservoir, these changes are gradual and continuous part of the long-term, dynamical exchange between the Sun's sphere of influence and the surrounding galaxy. In this environment, the comet that will later be recognized in observation as a single phantom remains one nucleus among many. It shares the same low temperature, the same slow orbital motion, and the same dark processed surface as its neighbours. Its path around the Sun is long and weakly bound, set by past scattering and by ongoing tidal influences. No gas surrounds it, no coma or tail marks its presence, and no direct observation singles it out. The outer cloud holds it in quiet storage along with countless similar bodies, as one element of a distant cold population that occupies the farthest known region of the solar system. Within the distant cloud of icy nuclei that surrounds the solar system, the motion of each body appears slow and stable when measured against human timescales. Orbits stretch over tens of thousands of astronomical units, periods extend over millions of years, and changes in position from one century to the next are small. Yet when the age of the solar system is considered, the cloud is not static. The positions and velocities of its members evolve under the combined influence of the Sun, the galaxy, and passing stars. These influences act gently but persistently, altering orbital shapes and orientations in ways that can, over long spans of time, move some bodies from distant, nearly circular paths into highly elongated ones that carry them toward the inner regions. The slow disturbance that begins this process is a key part of the accepted dynamical picture of how long-period comets enter the planetary zone. The galactic tide provides one of the main background influences on the Oort cloud. The Sun orbits the centre of the Milky Way galaxy, and the gravitational field of the galactic disk and halo varies with position. This large-scale field exerts a weak but steady pull on bodies in the outer cloud, adding a slowly changing component to the Sun's own gravity. The effect is strongest in the directions perpendicular to the galactic plane and along the radial line toward the galactic centre. Over many millions of years, this tidal field can change the inclinations and eccentricities of comet orbits, causing perihelion distances to drift inward or outward. For a given nucleus, the tide may lift the far end of its orbit slightly while lowering the near end or vice versa, reshaping the path without ejecting the body from the Sun's domain. Passing stars provide a second important source of perturbation. As the Sun travels through the galaxy, it encounters other stars at a range of distances. Most of these neighbours pass at many light years with small gravitational influence. A minority pass closer within a few light years or less, and these closer approaches can significantly disturb the orbits of bodies in the Oort cloud. When a star passes, its gravity adds a temporary acceleration to the nuclei in the cloud, slightly changing their velocities. The magnitude of this change depends on the mass of the star, its closest approach, distance and its relative speed. A single encounter rarely ejects large numbers of bodies. Instead, it alters the orbit of some, moving them into new configurations that the galactic tide then continues to shape. Over the age of the solar system, many such encounters occur, and their cumulative effect is to keep the outer cloud dynamically active. The combined action of the galactic tide and passing stars creates what is often called a loss cone in orbital space. Bodies whose perihelion distances are reduced below a certain threshold can enter regions where planetary perturbations or stronger solar heating become important. A nucleus in the Oort cloud starts with a perihelion so distant that it never approaches the planets. Under tidal and stellar perturbations, this perihelion can drift inward across a range of distances. For many bodies, the shift is modest and remains in the outer regions. For some, the change is large enough that their new orbits intersect the planetary zone. These bodies then become potential long-period comets that can be observed from the inner system once they move far enough inward that sunlight drives visible activity. In this way, the outer dynamics of the cloud provide a steady, though low supply of new comets to the inner regions. The time required for these changes is long. A single nucleus may spend hundreds of millions of years completing only a few orbits in the outer cloud, gradually experiencing the integrated effect of the galactic field and occasional stellar passages. During this time, its orbital energy with respect to the Sun remains roughly constant, but its angular momentum and orientation in space change. As angular momentum decreases, the perihelion distance shrinks, while the aphelion distance remains large. When the perihelion falls far enough, the inward part of the orbit enters the realm, where the Sun's radiation and the gravitational field of the planets begin to play stronger roles. The nucleus that will later be identified as a phantom comet follows this pattern. For most of its existence, it remains in the outer cloud, with slow secular changes in its orbital elements. Only when these changes accumulate sufficiently does its path intersect the inner solar system. A quiet detail of this region is that the disturbances are statistical rather than targeted. The galactic tide acts on all bodies in the cloud in a way that depends on their positions and velocities, but it does not single out any particular nucleus. Passing stars perturb some orbits more than others depending on geometry and timing, but which nuclei are strongly affected is a matter of chance within the larger distribution. Over long times, this randomness spreads the cloud's population through a range of orbital parameters. Some objects are nudged inward, others outward, some ejected entirely from the Sun's influence. The nucleus that becomes a phantom comet is not special at this stage. It is simply one among many whose orbit crosses the threshold into the loss cone region. There is a scientific uncertainty about the exact population and structure of the Oort cloud, which affects how often such perturbations send comets inward. Estimates of the total number of bodies, their size distribution, and their radial extent vary between models, and no direct imaging exists to constrain these values tightly. As a result, there is a range in the predicted rate at which long-period comets should appear in the inner solar system. Observed rates are broadly consistent with these estimates, but the match is not precise enough to fix all parameters. In particular, the detailed balance between galactic tides, stellar encounters, and the initial distribution of orbits remains an active topic of research. The phantom comet originates within these uncertainties as a single example, drawn from a population whose full characteristics are still being refined. Soft differences in orbital parameters determine the future of each nucleus under this slow dynamical evolution. Two bodies with similar initial semi-major axes and inclinations can experience different sequences of perturbations, leading one to remain in the outer cloud while the other is directed inward. The specific pattern of passing stars and galactic tidal phases that each nucleus encounters plays a role, as does its initial position within the cloud. Over periods long compared with the orbital period around the galaxy, these differences accumulate. The overall statistical properties of the cloud remain stable, but individual histories diverge. The nucleus that later appears as a phantom comet follows one such history, moving gradually from a nearly isotropic distant orbit toward a more elongated path whose perihelion lies deep within the planetary zone. As the orbit changes, the physical state of the nucleus remains almost unchanged. The temperatures in the outer cloud do not rise sufficiently to drive significant sublimation, and the surface retains the same dark, processed character described earlier. Internal structure, including porosity layering and trapped volatiles, also remains largely preserved. The orbital evolution acts on the path in space, not on the composition or internal energy of the body. From a physical standpoint, the nucleus is carried toward the inner solar system, still holding the mixture of ices and dust it acquired during formation and early processing. These materials will only begin to respond when the sun's radiation becomes stronger at smaller heliocentric distances. There is an additional source of perturbation from massive molecular clouds and other large-scale structures in the galaxy. When the solar system passes through regions of higher density in the interstellar medium, the combined gravitational field of the gas and any embedded stars can enhance the tidal forces acting on the Oort cloud. This can increase the rate at which orbits are changed, and may lead to temporary increases in the flux of long-period comets into the inner system. Evidence for such episodes remains indirect and model-dependent, and the timing and magnitude of past encounters are subjects of ongoing study. Whether the nucleus that becomes the phantom comet experiences such an enhanced phase or only the steady background of the galactic tide is not known. Both possibilities are consistent with its eventual inward scattering. From the perspective of the outer region, the essential change is that some nuclei transition from orbits that never approach the Sun closely to orbits that do. The region remains dominated by slow motions and low temperatures. No coma forms, no tails appear, and no direct observation singles out the bodies whose perihelia are shrinking. The dynamics are expressed only in incremental changes in orbital elements over very long times. The nucleus that will later be observed once as a phantom comet completes this transition gradually. Its path shifts from a distant, nearly symmetric loop to a more elongated curve with a closer approach to the Sun, carrying it into the next region of the story, where the heliosphere and the first effects of solar radiation become significant. As the comet's orbit evolves under galactic tides and stellar encounters, the point of closest approach to the Sun moves steadily inward. For most of its history, the nucleus spends almost all its time far beyond the region in which the solar wind dominates the surrounding space. The environment there is set by the local interstellar medium, a diffuse mixture of gas dust and magnetic fields that fills the galaxy. At some stage in its long trajectory, the nucleus reaches distances where it begins to cross the outer structures of the heliosphere, the region where the continuous outflow of plasma from the Sun displaces and shapes the interstellar medium around the solar system. This crossing does not occur at a sharp boundary, but over a broad zone where the properties of the plasma and magnetic field change gradually from interstellar to solar wind-dominated conditions. The heliosphere forms where the solar wind pushes outward until its pressure balances that of the surrounding interstellar gas. The solar wind is a continuous flow of charged particles, mainly protons and electrons emitted from the Sun's corona. It carries with it the solar magnetic field stretched into an extended structure by the rotation of the Sun. At large distances from the Sun, this flow slows as it encounters the interstellar medium. A region known as the termination shock marks where the supersonic solar wind decelerates to subsonic speeds. Beyond that lies the heliosheath, where solar and interstellar plasmas mix and adjust, before reaching the heliopause, the surface where the net flow changes from being predominantly solar to predominantly interstellar. Spacecraft observations have sampled these outer regions near the direction of the Sun's motion through the galaxy, but the overall shape of the heliosphere varies with direction and with time as both solar activity and the local interstellar conditions change. As the comet's nucleus moves inward from the distant Oort cloud, it eventually traverses these regions. At first, the change in environment is subtle from the nucleus's point of view. The ambient plasma density increases compared with the interstellar background, and the dominant magnetic field shifts from the galactic to the solar configuration. The energy spectrum of charged particles also changes with galactic cosmic rays, becoming partially shielded by the heliospheric magnetic field and by the solar wind. This modulation of cosmic rays is a known effect at smaller heliocentric distances. The flux of the highest energy particles is reduced compared with values in the local interstellar medium. For the nucleus, this means that the rate at which its surface is processed by such particles decreases somewhat as it enters deeper into the heliosphere. The gas and dust that surround the nucleus remain extremely sparse during this phase. The surface temperature is still very low since the Sun, though brighter than it appeared in the outer cloud, is still a distant star delivering only a small amount of energy per unit area. Water ice and most other volatiles remain solid, with only negligible sublimation. The nucleus continues to travel as a compact body with no extended coma or tail. Any gas molecules or small particles released by micrometeoroid impacts or by weak thermal processes are quickly swept away by the solar wind, joining the general population of ions and dust that fills interplanetary space. The influence of the solar magnetic field on charged particles released near the nucleus becomes more important than the influence of the galactic magnetic field. Newly ionized atoms produced by interactions with ultraviolet photons or by charge exchange with solar wind ions are picked up by the solar wind and carried along its flow lines. These pickup ions add mass and momentum to the wind, a process observed near active comets closer to the Sun, but even at large distances some level of interaction occurs. For the phantom comet's nucleus at this stage, however, the number of such particles remains very small, and no large-scale plasma structure forms around it. The interplanetary magnetic field carried by the solar wind has a spiral pattern due to the Sun's rotation. At the distances where the nucleus now travels, this field is relatively weak but still structured. The orientation and strength of the field vary with heliographic latitude and with the phase of the solar activity cycle. As the nucleus moves inward along its inclined orbit, it passes through regions where the magnetic field orientation changes gradually, and where the properties of the solar wind shift between slower and faster streams. These variations influence how any ionized material near the nucleus would move, but the overall effect on the solid body is limited to minor contributions to surface processing and to the trajectories of any charged dust grains. A scientifically accepted feature of the heliosphere is that its size and internal structure respond to changes in the solar wind's pressure over the cycle of magnetic activity. When the Sun is more active, the average pressure of the wind increases, pushing the heliopause outward. When the Sun is quieter, the boundary can move inward. As a result, the distance at which the comet's orbit intersects the termination shock or the heliopause depends on the phase of the solar cycle at the time of crossing. Over the long interval of its orbital evolution, the nucleus may encounter different configurations of the heliosphere. These changes, however, do not significantly alter its overall trajectory, which is still controlled mostly by gravity, but they do modulate the particle environment through which it moves. The surface of the nucleus responds slowly to these changing conditions. The reduction in galactic cosmic ray flux inside the heliosphere lowers the rate at which new radiation-processed layers form, but previous layers remain intact. The dark, organic, rich crust that formed during the nucleus's long residence in the Oort cloud continues to cover the underlying ices. Small impacts from interplanetary dust, whose population increases closer to the Sun, can chip away at this crust and expose fresh material, but such impacts are infrequent and localized at these large distances. The net result is that the nucleus retains most of its inherited structure and composition, while its orbit carries it through the outer heliosphere. In terms of the outer to inner progression, this region marks a shift from a dominantly galactic environment to one shaped by the Sun's continuous outflow. The nucleus is now surrounded by solar wind plasma rather than the undisturbed interstellar medium. Its path is influenced by the interplanetary magnetic field rather than by the larger-scale galactic one when it comes to charged particles. Yet the body itself remains cold and largely inert. No observational signature distinguishes it from many other small bodies at similar distances. From the perspective of observers near Earth, it is still too faint to be detected with present instruments, and its inward motion remains unnoticed. there is an uncertainty in how many comets may be crossing the outer heliosphere at any given time. Models of the Oort cloud and of the rate of comet injections suggest that several or more nuclei may be on inbound trajectories that will eventually carry them into the planetary region, but their exact number and positions are not known. The Phantom Comet's nucleus is one such object following a path set by its initial scattering and subsequent perturbations. Its crossing of the heliosphere's outer boundaries is an unremarkable event dynamically, yet it signifies that it has left the purely galactic regime and entered a space where solar processes will progressively dominate its physical evolution as it continues inward. As the heliocentric distance decreases further, the energy received from the Sun will eventually reach levels where sublimation of the most volatile ices begins to rise measurably, and where the first sustained gas flow can develop around the nucleus. At the stage described in this section, however, the nucleus remains a compact dark body, moving through a changing plasma and magnetic environment, with only minimal outgassing and no extended atmosphere. The region of principal interest is the transition itself from interstellar to heliospheric conditions, which sets the background against which all later more visible activity will take place as the comet advances towards smaller distances from the Sun. As the comet moves further into the heliosphere, the Sun still appears as a small bright point in a dark sky, yet its influence at the nucleus begins to change the surface in a clear physical way. The distance from the Sun is still many tens of astronomical units, so the incoming energy remains low compared with that received by the inner planets, but it now exceeds the level that held the nucleus in almost perfect thermal balance in the distant cloud. The mean surface temperature rises by only a few degrees, remaining far below the melting point of water ice, yet this small increase is enough for the most volatile ices near the surface to begin to sublimate in a sustained manner. Carbon monoxide, carbon dioxide, and similar species gain sufficient energy that individual molecules can leave their binding sites and escape into the surrounding vacuum. In this regime, the nucleus changes from a completely dormant body into one that releases a continuous though very weak flow of gas. The energy balance at the surface governs this early activity. Sunlight arrives and some fraction is reflected while the rest is absorbed by the dark, low albedo surface. The absorbed energy is shared between re-radiation, as thermal emission, and the latent heat required to sublimate ices. Because the rate of sublimation depends very strongly on temperature, even a modest increase in absorbed power can raise the number of escaping molecules significantly. At the distances considered here, the resulting gas flux is still small when measured per unit area, but across the entire surface of a kilometre-scale nucleus, it produces a measurable total output. The gas forms an extremely thin envelope above the nucleus with density highest, immediately over the most illuminated regions and dropping rapidly with distance. The outermost layer of the nucleus plays a central role in how this gas reaches space. Over billions of years in the Oort cloud radiation has processed the surface into a dark crust enriched in refractory material and complex organic compounds. Ices are present in pores beneath this crust and along fractures within it. As volatile molecules sublimate, they move through this porous network, following paths of least resistance toward the vacuum. Gas escapes more easily through open fractures, vents and regions where the overlying dust is loosely packed, while areas sealed by denser or more cohesive material allow little flow. As a result, the first activity is spatially uneven. Some patches of the surface release gas at a higher rate, while others remain nearly inactive at the same heliocentric distance. The rotation of the nucleus adds a temporal pattern to this spatial structure. As the body turns, different regions enter and leave sunlight. Surfaces facing the Sun warm slightly and produce more gas, while those rotating into darkness cool and fall quiet. If the spin axis is tilted relative to the orbit, some latitudes experience longer seasons of illumination than others, so the pattern of activity can change gradually as the comet progresses along its path. For most long-period comets arriving from the Oort cloud, including those seen only once, the exact spin state is unknown, because they are too faint at these distances for detailed light curve measurements. Nevertheless, general models show that rotation can cause the earliest activity to appear in intermittent, slowly shifting patches rather than as a uniform shell. Heat does not penetrate far into the interior in a single rotation. The thermal conductivity of a porous, dusty mixture is low, so daily temperature changes affect only a shallow layer. Below this thin active zone, temperatures remain close to their primordial values. Over longer intervals, however, a small amount of heat can diffuse inward, gradually warming deeper ices. Some of the most volatile species can migrate along pores and cracks, moving from slightly warmer regions to colder ones where there are freeze. This migration can enrich certain depths in particular volatiles and deplete others near the surface. Laboratory experiments and numerical simulations explore these processes, but the exact structures they produce inside kilometre-sized nuclei remain uncertain. For the Phantom Comet, no direct measurements exist. Its internal rearrangement during this phase is inferred by analogy with other comets and with model results. The escaping gas carries momentum. When large numbers of molecules leave the surface in preferred directions, the net momentum loss can act as a weak thrust on the nucleus. At this stage, the total gas production is low, so the corresponding non-gravitational acceleration is very small compared with the Sun's gravity, yet it is not strictly zero. In principle, over many years of inward travel, such forces can shift the orbit slightly, changing the precise position of perihelion or the timing of arrival by small amounts. For comets with long observational arcs closer to the Sun, these non-gravitational terms can be fitted in orbital solutions. For a body still far beyond the region of regular observation, they lie below detection thresholds and remain part of the unmeasured background that adds uncertainty to any future orbit reconstruction. A further consequence of sustained sublimation is the development of a dust lag on the surface. Gas flow can lift and carry away fine grains, especially those with low cohesion and small mass. Larger grains, aggregates, and more strongly bound particles tend to remain. Over time, the uppermost layers become gradually richer in dust and poorer in exposed volatile ice. This dustier surface acts as an insulating blanket, reducing the efficiency with which heat penetrates to still volatile rich material below. At the same time, cracks, fractures, and weak zones in the crust can still provide channels where gas accumulates until it can escape, sometimes opening local vents. The balance between dust removal, dust retention, and the opening of new pathways helps determine whether early activity increases smoothly with decreasing heliocentric distance, or occurs in small steps as pockets of gas find new exits. Even in this early regime, the escaping gas interacts with solar radiation. Molecules leaving the surface can absorb ultraviolet photons and dissociate into fragments. Some of these fragments become ions, which are then picked up by the solar wind and carried away along the interplanetary magnetic field. Others recombine into new neutral species. The total number of particles is low compared with later stages, so no bright ion tail forms, but chemically the environment near the nucleus already contains a mixture of original volatiles and their first-generation products. If a spacecraft were present, it could in principle measure these ratios and infer details about the composition of the underlying ices. In practice, no such measurements exist for long-period comets at these distances, leaving this phase mostly described by theory and by analogy with closer observations. There is a clear scientific uncertainty about the exact heliocentric distance at which different volatile species begin to show sustained sublimation on typical long-period nuclei. The onset distance depends on the composition porosity rotation rate and local topography of each comet. Observations of a small number of objects suggest that activity driven by very volatile ices can begin at distances of several tens of astronomical units, while water ice usually becomes important much closer in. For the nucleus that will later be classified as a phantom comet, the exact onset of activity is not recorded. Its first surface changes under solar heating take place unobserved, governed by the same general physical laws but modulated by individual properties that remain unknown. In terms of the outer to inner progression, this stage marks the first sustained departure from the almost static conditions of the distant cloud. The comet still appears from afar as a small unresolved point with no obvious coma, yet the surface no longer behaves as a perfectly inert shell. Low-temperature volatiles now leave the upper layers in a continuous flow. A thin envelope of gas develops near the nucleus, and the structure of the outer crust begins to adjust to the new energy balance. The nucleus carries forward the materials it acquired during formation, but their arrangement and state are no longer fixed. As the comet proceeds inward along its elongated orbit, this early activity prepares the surface, a near subsurface, for the more intense heating that will occur at smaller heliocentric distances, where additional ices will join the flow and the observable coma will begin to form. As the comet moves inward along its elongated orbit, the sunlight at its surface grows steadily stronger, although the distances involved still place it far beyond the inner planets. The nucleus has already begun to release the most volatile ices in a weak but continuous flow. As the heliocentric distance decreases further, the energy input rises enough that gas production increases by several orders of magnitude compared with its earliest activation in the outer cloud. The gas now leaves the surface in quantity sufficient to build up a surrounding envelope, whose density, while still extremely low by atmospheric standards, is high enough that particles begin to collide with one another before they escape. This region of bound gas around the nucleus is the nascent coma, an extended, roughly spherical atmosphere sustained not by gravity alone, but by a balance between production at the surface and outflow into space. The coma forms because the time it takes for molecules to travel away from the nucleus becomes longer than the time between collisions near the surface. Close to the nucleus, where the gas density is highest, molecules scatter off one another, exchanging energy and momentum. This collisional regime allows the inner portion of the coma to behave in some ways like a very tenuous fluid. Temperature and density gradients develop shaped by the distribution of active areas on the surface, and by the rotation of the nucleus. Farther out, as the density decreases with distance collisions, become rare, and the gas transitions into a free molecular flow where individual particles follow nearly ballistic trajectories. The boundary between these regimes does not occur at a sharp radius, but over a range where the mean free path becomes comparable to the scale of the coma. At this stage, water ice may still play only a minor role in driving activity, if the comet remains in the cold outer regions beyond the orbit of Jupiter. The main contributors to the gas flow are often more volatile species such as carbon monoxide and carbon dioxide, whose sublimation rates at low temperatures are high enough to maintain significant outgassing. These molecules carry away latent heat from the surface, helping to regulate the temperature of the outer layers. As gas escapes, it entrains solid particles from the nucleus, lifting fine dust grains out of pores and fractures. The amount of dust carried depends on the local gas flux and the cohesion and size distribution of particles. In some areas, gas flow is strong enough to remove surface dust and expose fresh ice, while in others a layer of residual dust accumulates, forming an insulating mantle that reduces further sublimation. The growing coma interacts with sunlight in several ways. First, dust particles in the inner coma scatter visible light. Even at large heliocentric distances where gas production is relatively modest, the combined cross-section of many small grains can reflect enough sunlight to make the coma detectable if it is observed with sensitive instruments. The surface brightness of the coma decreases rapidly with distance from the nucleus, so the inner region appears brighter and more condensed. As the comet continues inward and production increases, the coma grows both in physical size and in overall brightness, though in this stage it remains compact compared with the enormous comae seen near perihelion. Second gas molecules absorb ultraviolet photons and may re-emit them at characteristic wavelengths, contributing faint emission lines and bands to the coma's spectrum. These spectral features provide information on the composition of the gas, and are used in observations of comets nearer the Sun. The dynamical structure of the coma reflects the combination of gas expansion, nucleus rotation, and solar illumination. gas leaves the surface with thermal velocities that depend on the local temperature and molecular mass. In directions where the surface is more strongly heated, the gas density and outflow speed are higher. Rotational motion causes active regions to sweep through different solar zenith angles, modulating the coma's brightness and anisotropy over the rotation period. Even at large distances, anisotropic outgassing can create jets and fans regions of enhanced brightness within the coma that extend away from the nucleus along specific directions. These features are more prominent closer to the Sun, but their beginnings are rooted in these early relatively cold stages when the first sustained gas flows emerge. The surrounding solar wind also influences the coma. As neutral gas expands outward, some fraction is ionized by solar ultraviolet photons or by charge exchange with solar wind ions. The newborn ions experience electromagnetic forces, causing them to be picked up and carried along with the solar wind. This process extracts momentum from the wind and transfers it to the coma, creating a region of disturbed plasma around the comet. Even when the gas production is still modest, the interaction region begins to take shape. A bow wave or shock can form upstream depending on the relative speeds and pressures, and a wake region develops downstream. The detailed structure of this interaction is complex and depends on gas production, rate solar wind conditions, and the comet's motion. But the basic picture of an expanding neutral coma interacting with a flowing plasma is supported by both theory and spacecraft observations at other comets. Within the coma, chemical evolution proceeds as molecules are exposed to radiation. Primary volatiles released from the nucleus break apart into daughter and granddaughter species under ultraviolet light. For example, water molecules can dissociate to form hydroxyl radicals and hydrogen atoms. Carbon monoxide and carbon dioxide can produce atomic carbon and oxygen. The abundances and spatial distributions of these products depend on the rates of photodissociation, the expansion speed of the gas, and the local radiation field. Although the phantom comet's coma at this stage is not directly sampled, the same processes are expected to occur, transforming the original composition into a mix of primary and secondary species as the gas flows outward. The dust component of the coma plays a separate but related role. Grains lifted from the surface have a range of sizes and compositions, their temperatures just to the balance between absorbed sunlight and emitted thermal radiation. Small grains can reach higher temperatures than the bulk nucleus, because they radiate less efficiently at longer wavelengths, while larger grains stay somewhat cooler. If grains retain volatile coatings or embedded ices, they can themselves become small sources of gas as they travel through the coma, adding a distributed source term that supplements the direct outgassing from the nucleus. Over time, grains move outward under the combined influence of gas drag gravity and radiation pressure populating the outer coma, and contributing to the eventual formation of dust tails at smaller heliocentric distances. The extent of the coma is set by the balance between gas production and expansion speed. Typical expansion velocities for gas in these outer regions are on the order of several hundred meters per second, increasing somewhat as the comet approaches the Sun and the gas temperature rises. If the production rate is sustained, molecules can travel many thousands of kilometers before their density falls to negligible levels. The resulting coma radius can reach tens or hundreds of thousands of kilometers even when the nucleus itself is only a few kilometers across. The density within this volume remains extremely low compared with any planetary atmosphere, but it is enough to create an observable feature against the dark background of space. There remains a scientific uncertainty in the detailed structure of comae at large heliocentric distances, because relatively few comets have been observed in this regime with sufficient resolution and sensitivity. Most observational data focus on comets closer to the Sun, where activity is stronger and features are easier to detect. As a result, models of the early cold coma rely heavily on extrapolating physical laws and on limited measurements. They predict that activity at these distances is dominated by the most volatile species, that comae are relatively compact and low in brightness, and that dust loading may be lower than at smaller distances. For any specific long-period comet, including the one that will later be classified as a phantom, These general expectations must stand in for detailed observations. Within the outer to inner progression, this stage represents the first clear development of an extended atmosphere around the nucleus that is shaped by the balance of outgassing solar radiation and the surrounding solar wind. The comet is still in a cold part of the solar system, but the coma has grown enough to form a distinct region of gas and dust that surrounds the nucleus and responds to both local and solar-scale processes. The nucleus continues to carry its original mixture of ices and dust inward, but now it does so within an envelope that increases in size and complexity as the comet moves toward regions of higher solar flux. The coma marks the transition from a purely solid body travelling through space to a coupled gas and dust system, setting the conditions that will govern later stronger activity closer to the Sun. As the comet travels further inward, it enters the region of the solar system, where the giant planets circle the Sun, and where solar energy at its distance becomes strong enough that water ice, not only the most volatile species, begins to contribute significantly to its activity. The heliocentric distance has decreased to a point where the sunlight at the surface is many times more intense than in the outer cloud, but still less than that experienced by the inner terrestrial planets. Under these conditions, sunlit areas of the nucleus reach temperatures at which water molecules can sublimate in a sustained way. This change in the dominant volatile alters both the total gas production and the character of the coma. Gas flow from the nucleus increases substantially, and the relative contribution of different ices shifts as the balance of sublimation responds to the new local energy environment. With water sublimation now active, the total outgassing rate scales steeply with further decreases in distance. Water ice has a strong temperature dependence, and as the comet moves along its orbit towards smaller heliocentric values, small increases in absorbed energy lead to large increases in vapor pressure. Regions of the nucleus that previously released only carbon monoxide or carbon dioxide now add water vapor to the gas flow whenever the surface crust allows heat to reach underlying ice. The coma becomes denser near the nucleus and expands more vigorously outward. Gas expansion speeds increase, and the transition between the collisional inner coma and the more rarefied outer coma moves to larger radii. The gas-dominated region grows, and its structure acquires stronger gradients in density and temperature shaped by solar illumination and rotation. The increasing gas production has a direct effect on dust entrainment. Stronger gas flows exert larger drag forces on particles near the surface. Grains that previously remained bound within the uppermost layers can now be lifted free and carried away. Fine dust particles with small masses and large surface areas are the easiest to move, but as activity intensifies, larger aggregates can also be dislodged. The inner coma becomes more heavily loaded with dust, and the optical appearance of the near-nuclear region is now dominated by scattered light from these grains. In images, this behavior appears as a bright central condensation surrounding the unresolved nucleus, with brightness profiles that fall off more slowly with distance than those of a purely gaseous coma. The pattern of active areas on the surface combined with the rotation of the nucleus produces organized structures in the coma. Localized vents or fractured regions where sublimation is particularly strong act as sources of discrete gas flows. As the nucleus spins, these jets sweep through space-carving spiral or fan-shaped density enhancements into the expanding coma. In the inner regions where collisions between molecules are frequent, these structures can appear as curved ridges or sector-shaped regions of higher brightness. Farther out, where the gas becomes more collisionless, the same jets delineate narrow features that extend away from the nucleus before merging into the general flow. Other comets observed at similar distances display such jets and fans, and the same physical processes are expected to operate for the phantom comet, even though no images record its specific geometry. Asymmetric outgassing now begins to play a more noticeable role in the dynamics of the nucleus. When gas escapes preferentially from certain areas, the recoil force acts as a small thrust, altering the comet's motion slightly beyond what gravity alone would predict. Near the region of the giant planets, this non-gravitational acceleration remains small compared with the Sun's pull, but its cumulative effect over months of strong activity can produce changes in the orbit that become detectable when precise positional data are available. For comets observed over many apparitions, these effects can be fitted as additional terms in orbital models. For a long-period comet that will be seen only once they contribute to the uncertainty in any reconstructed path. The phantom comet's precise non-gravitational history at this stage is not known, but it is governed by the same balances between gas production, active area distribution, and rotational state that apply to other nuclei. The surrounding solar wind becomes increasingly important in shaping the outer regions of the coma as the comet approaches the inner system. Neutral gas expanding outward from the nucleus is ionized at higher rates than in the distant heliosphere, feeding a population of cometary ions that are picked up by the solar wind. This process slows and deflects the local flow, forming a disturbed region upstream and a magnetized wake downstream. The boundary where the pressure of the cometary ions and magnetic field balances that of the undisturbed solar wind moves outward as gas production grows. Inside this boundary, cometary plasma dominates. Outside it, the solar wind remains largely unmodified. The increase in coma size and density enhances the role of photochemistry. With more gas present, the integrated column density along lines of sight through the coma grows, and the rates at which molecules are transformed by ultraviolet photons rise. Distinct regions with different dominant species appear very close to the nucleus primary. Volatiles remain most abundant. Farther out, their dissociation products become more common. These spatial gradients depend on the ratio of photodissociation timescales to expansion timescales, and they develop naturally as gas flows outward under radiation. For the phantom comet, such gradients would be present, even though no observations sample them directly. At these distances, the comet may also begin to feel gravitational perturbations from the giant planets, in a more pronounced way. If its orbit brings it near Jupiter or Saturn, even without a very close encounter, their masses can alter its path, slightly changing parameters such as inclination or eccentricity. These changes occur in addition to any non-gravitational shifts produced by outgassing. Exact outcomes depend on the geometry and timing of the passage, and for the phantom comet, the limited observational arc leaves this part of its history uncertain. It remains one example of how long-period comet orbits can be adjusted as they traverse the region dominated by the large planets. Despite these complexities, the overall trend as the comet approaches the inner system is straightforward. The nucleus experiences steadily increasing solar flux, driving stronger and more extensive outgassing. The coma grows in size density and structural complexity, with jets, fans, and anisotropies reflecting conditions on the surface. The interaction with the solar wind establishes a region of disturbed plasma around the comet, while photochemical processes modify the composition of the gas as it expands. Dust entrainment increases, preparing the material that will form well-developed dust tails at smaller heliocentric distances. Within the outer to inner framework, this stage still lies outside the very inner planetary region, but it marks the comet's transition into a domain where it begins to manifest the organized structures that characterize active comets seen from Earth, while gas and dust are increasingly ready to separate into distinct tail components as the inward track continues. As the comet continues inward and the coma becomes rich in gas and dust, the sunlight that drives sublimation also begins to separate the paths of solid particles from those of the gas. Neutral gas molecules once released from the nucleus feel gravity from the sun and expand outward in all directions until they are ionized or dispersed. Dust grains, by contrast, respond both to gravity and to the pressure of sunlight itself. Each photon that strikes a grain transfers a small amount of momentum, and over time this continuous push alters the grain's motion. The effect is strongest for small particles with large surface area compared with mass. Under these conditions, dust no longer simply rides outward with the gas. It begins to follow its own trajectories, forming structures that extend away from the nucleus on scales much larger than the coma. Near the nucleus, dust grains are lifted from the surface by gas drag. The gas flow emerging from active areas pushes against the grains embedded in the surface layers. If the drag force exceeds the combination of gravity and cohesive forces holding a grain in place, the grain is detached and accelerated away from the nucleus. Fine particles with sizes in the micrometer range are easily moved. Larger grains require stronger gas flows or more favourable local conditions. Once free of the surface and carried some distance into the coma, grains begin to decouple from the gas flow. Their inertia and the declining gas density allow them to move under the combined influence of the sun's gravity and radiation pressure. Radiation pressure effectively reduces the net gravitational pull of the sun on a dust grain. The magnitude of this reduction depends on the grain size, composition and shape. For very small grains, the pressure force can be a significant fraction of the gravitational force and in some cases comparable to it. For larger grains, gravity remains dominant and radiation pressure acts only as a small perturbation. The ratio of these forces determines how strongly the grain's path deviates from that of the nucleus. In general, the smaller the grain, the more its trajectory is pushed outward away from the sun and away from the orbit that the nucleus follows. As a result, a population of grains released near the comet spreads out into a broad curved structure. Grains with different sizes released at different times and from different points on the nucleus follow slightly different paths. Those with weak coupling to radiation pressure stay relatively close to the orbital track, forming a trail of dust that lags behind the comet along its path. Those with stronger coupling are pushed more directly away from the sun, forming a fan-shaped structure that extends outward from the coma. When sunlight illuminates this collection of grains, the combined scattering produces the optical feature known as the dust tail. It is not a continuous solid object, but an ensemble of many particles, each moving independently according to its own balance of forces. The geometry of the dust tail is governed by the relative motion of the comet and the direction of sunlight. At any given moment, the pressure from sunlight acts along the line from the sun through each grain. The comet, however, moves along its orbit with a velocity that has both radial and tangential components. Grains released from the coma inherit the nucleus's orbital speed, and then experience an additional outward acceleration due to radiation. Over time, this combination of initial velocity and persistent acceleration produces an arc in which dust grains appear to trail behind the comet and curve away from the direction of motion. The curvature of the tail reflects the history of dust release. Older grains released when the comet was at larger heliocentric distances occupy outer parts of the tail. Younger grains shed more recently remain near the coma. Closer to the nucleus, the dust distribution still retains the imprint of the gas jets and active regions that lifted the grains in the first place. Narrow features in the coma can extend into the base of the tail, forming streamers in which the density of grains is higher than in the surrounding regions. As the comet rotates, the orientation of these jets changes, gradually populating the tail with particles on a range of trajectories. Over longer times, the fine structure partially smooths out due to the combined effects of differential motion and varying radiation pressure, but the near-nucleus region can retain visible jet-like enhancements. The detailed shape and brightness of these structures depend on the rotation period and active area distribution and gas production rate, all properties that remain unmeasured for the phantom comet, but that follow common physical principles. The dust tail's brightness arises from solar light scattered by the grains. The intensity of scattered light depends on grain size composition and the angle between the sun, the grain, and the observer. In regions where many small grains are present, the scattering can be strong, making those parts of the tail more luminous. Larger grains, though more massive, contribute less to the brightness per unit mass, because their total scattering cross-section is smaller, relative to their weight, and they often concentrate closer to the orbital track rather than spreading widely. Across the tail, these differences produce a gradient in both brightness and colour. In observations of other comets, dust tails tend to appear slightly reddened compared with the solar spectrum, consistent with the presence of silicate and carbon-rich grains. The phantom comet's dust tail would be shaped by similar factors, though its precise spectral properties remain unrecorded. Non-gravitational forces arising from dust emission can act back upon the nucleus. As grains are ejected preferentially in certain directions, the reaction force can slightly alter the spin state or orbital motion of the comet. Over short times near perihelion, these effects are usually modest, but over many passages they can be significant. For long-period comets that pass only once through the inner system, within observational records including the Phantom Comet, such feedback remains part of the unmeasured component in their dynamics. The main observable consequence lies in the dust tail itself, which records the pattern of ejection through its shape and density distribution. The dust tail also gradually evolves into a dust trail along the orbit. Grains with low radiation pressure coupling especially larger particles remain close to the nucleus's path as the comet moves along its orbit and then away from the Sun. These grains spread out with time, forming a narrow band of material that can persist for many revolutions if the comet is bound, or for long distances along an escape trajectory if it is not. The trail is less obvious in scattered light than the immediate tail seen near perihelion, but it carries much of the mass that the comet loses in solid form. Over geological timescales, repeated deposition of such trails from many comets contributes to the broader population of interplanetary dust in the inner system. There is a scientific uncertainty in the detailed size distribution of dust grains produced by individual comets, particularly long-period ones that are observed only briefly. Spacecraft encounters with a few short-period comets and in situ dust measurements provide some constraints, but generalizing these results to all comets is limited by the diversity of compositions and histories. For the Phantom Comet, no direct dust measurements exist. Its dust tail and trail must be described using the established pattern that outgassing and radiation pressure generate a mixture of grains that populate both a wide curved tail and a narrower orbit-hugging trail. The exact balance between these components remains unknown but is constrained by the physics of gas drag grain cohesion and radiation forces. Within the outer to inner progression, this stage marks a key transition in the visible structure of the comet. Previously, gas and dust in the coma formed a largely symmetric envelope around the nucleus. Now, radiation pressure has introduced a directional asymmetry into the dust distribution, pulling grains away from the Sun and stretching them into an extended tail. The nucleus continues to release gas and dust as it moves inward, but the dust no longer simply fills the coma. It organizes into a structure that carries information about grain properties, outgassing patterns, and the geometry of the orbit. The comet remains at distances where solar heating is still increasing, and the dust tail will continue to grow in length and complexity as more grains are added, and as the inward journey progresses towards smaller heliocentric distances. Closer to the Sun, where the coma is dense enough and gas production strong enough, the interaction between the comet and the solar wind develops a distinct large-scale structure. Neutral molecules that leave the nucleus expand outward, and a fraction of them are ionized by solar ultraviolet radiation, or by charge exchange with ions carried in the solar wind. Once a neutral atom or molecule loses an electron and becomes an ion, it begins to respond strongly to electromagnetic forces. The interplanetary magnetic field, frozen into the flowing solar wind, exerts a Lorentz force on these new ions, accelerating and guiding them along the magnetic field lines. In this way, material that initially expanded almost isotropically from the nucleus becomes organized into a directed flow that points roughly away from the Sun. The result is the ion tail, a distinct component of the comet's environment that differs from the dust tail in both structure and physical origin. Near the nucleus, neutral gas still dominates. The density of molecules is high enough that collisions remain frequent, and the flow behaves in a fluid-like way. Ionization events occur throughout this inner coma, converting a small fraction of the neutrals into ions and electrons. These new charged particles are quickly picked up by the solar wind. Because the solar wind streams past the comet at speeds of several hundreds of kilometers per second, much faster than the expansion speed of the neutral gas, the ions experience a rapid change in reference frame. They are accelerated from near rest relative to the comet into co-motion, with the solar wind following spiral paths around the magnetic field lines while being carried downstream. This process adds mass to the solar wind flow and modifies its velocity and magnetic field configuration near the comet. The region where the solar wind first encounters the expanding coma is known as the interaction zone. As the comet approaches the Sun and its gas production increases, the density of neutrals in this zone rises. The addition of new ions through charge exchange and photoionization increases the local plasma density and changes the effective Alfvén speed, which is the characteristic speed at which magnetic disturbances propagate in a plasma. When the solar wind slows from super-Alfvénic to sub-Alfvénic flow, relative to the comet, a bow shock, or a more gradual bow wave, can form upstream of the nucleus. Across this boundary, the solar wind's speed and direction adjust, and the magnetic field is compressed and draped around the cometary obstacle. Spacecraft encounters with several comets have detected such bow structures, confirming this general picture of interaction. Inside the bow region, a contact surface separates the shocked solar wind plasma from plasma dominated by cometary ions. This region, often called the diamagnetic cavity, when it develops fully, is characterized by a reduction in magnetic field strength near the nucleus, maintained by the pressure of the outflowing cometary plasma. The cavity's size depends on gas production rate and solar wind conditions. At high activity levels near perihelion, it can extend over distances comparable to several times the nucleus radius. At lower activity levels, it may be small or transient. For a long period, comets, such as the one described here with only a single observed apparition and no spacecraft measurements, the detailed size and persistence of such structures remain unmeasured. Nevertheless, the same physical balances between plasma pressure, magnetic field pressure, and gas production apply. Beyond the cavity, the interplanetary magnetic field lines are draped around the comet bent, as they are forced to flow around the obstacle presented by the expanding coma. Cometary ions, once created, spiral along these bent field lines and are carried downstream. The direction of the ion flow is set not only by the radial line away from the Sun, but also by the orientation of the magnetic field and the relative motion between the comet and the solar wind. In many cases, the resulting ion tail points close to the anti-solar direction, appearing as a narrow, relatively straight feature that differs from the broader, more curved dust tail. Its internal structure can contain rays, knots, and fine filaments, where variations in plasma density and magnetic field strength concentrate or disperse the ions. The length of the ion tail can reach millions of kilometers, limited in practice by the rate at which ions are lost through recombination charge exchange or mixing with the solar wind, and by the sensitivity of observations. Within this extended structure, gradients in ion composition reflect the history of outgassing and photochemical processing in the coma. Close to the nucleus, recently ionized species remain more abundant, while farther downstream, the distribution shifts toward products of further reactions and interactions. The tail thus records in its spatial structure a combination of time history and current solar wind conditions. For the phantom comet, no direct sampling of this tail exists, yet the same processes would have governed its formation and maintenance. The interaction between the ion tail and varying solar wind conditions introduces additional complexity. The solar wind is not uniform. It contains fast and slow streams shock fronts and changes in magnetic field direction associated with solar rotation and activity. When a change in the interplanetary magnetic field passes across the comet, the draped field lines in the tail can reconnect or rearrange. In some cases observed at other comets, this process has led to tail disconnection events where the visible ion tail suddenly detaches and a new one begins to form aligned with the updated magnetic field configuration. The plasma physics of such events involves magnetic reconnection and the propagation of disturbances along the tail. For the phantom comet, similar processes might occur, but whether any such disconnections happened during its passage is not known. There is a scientific uncertainty in the precise boundary shapes and field configurations within each cometary interaction region. While general features such as bow shocks, magnetic draping, and ion pickup have been confirmed by spacecraft data at a small number of comets, the exact geometry depends sensitively on solar wind pressure, magnetic field orientation, and cometary gas production at a given time. Long-period comets, which are often observed only from a distance, and for limited intervals have fewer constraints on their plasma environments. For the object in question, the interaction must be described in terms of the established framework rather than in terms of specific measured values. The energy exchange between the solar wind and the comet's plasma environment also affects the dynamics of the ions. Newly created cometary ions start at low energies in the comet's frame, but are accelerated by the electric field associated with the moving solar wind and magnetic field. As they gain energy, they contribute to the heating and momentum balance of the local plasma. Some of this energy is carried away downstream in the ion tail. Some is transferred back to the solar wind as the flow is decelerated and mass loaded. Over the course of the comet's passage through the inner system, this continuous interaction represents a small but non-zero modification of the solar wind flow in the comet's vicinity. Within the ion tail, the density and composition of plasma vary across its cross-section. Closer to the central axis, where field lines are more tightly draped and the flow of new ions its strongest densities are higher. At the edges, mixing with the ambient solar wind reduces the concentration of cometary material. Small-scale instabilities such as Kelvin-Helmholtz or other shear-driven modes may develop along the interface between tail plasma and surrounding solar wind, leading to waves, vortices, and irregular structures. These instabilities can contribute to the fine filamentary appearance observed in some tails. Without direct imaging of the phantom comet's tail, these features remain part of the general behavior inferred from other cases. Within the outer to inner sequence, this stage is defined by the establishment of a clear plasma structure, aligned with the solar wind and magnetic field, extending away from the nucleus, and distinct from the quasi-isotropic neutral gas and the radiation pressure-driven dust. The comet now possesses three main components: a neutral coma expanding outward a dust distribution shaped into a curved tail by radiation pressure, and an ion tail guided by fields and plasma flows. The focus here remains on the ion component, which forms as neutral molecules become charged and are incorporated into the solar wind, creating a long, narrow region of cometary plasma directed roughly away from the Sun. As the comet continues along its orbit at these distances, this ion tail adjusts continuously to changing solar wind conditions, maintaining the overall pattern of a magnetized flow that links the near-nucleus environment to regions millions of kilometers downstream. As the comet moves through the inner region of the solar system and its coma and tails brighten under stronger sunlight, it finally becomes detectable from one small planet, with a long practice of watching the sky. At first, the object appears only in the field of telescopes, a faint diffuse patch recorded during routine surveys or directed searches. The night sky is treated as a precise coordinate grid, and every measurable point of light can be assigned a position on that grid. For astronomers, the presence of a comet is established not by its internal structure or its detailed plasma environment, but by a series of positions recorded against background stars at known times. The measurements begin when the comet's brightness crosses the limiting magnitude of the instruments in use, often while it's still far from the Sun compared with the inner planets, but much closer than the outer reservoir from which it came. At the eyepiece or on a detector, the comet's appearance differs from the stars. Stars at the distances involved are effectively point sources of light, producing sharp images limited only by the optical system and atmospheric seeing. The comet, with its coma of dust and gas, appears extended with a core that is brighter than its surrounding envelope but not sharply edged. Early in its apparition, this central condensation may be only marginally resolved, with a slight fuzziness that distinguishes it from a star. As activity increases, the coma expands, and a short tail may become visible oriented roughly away from the Sun. These qualitative features help identify the object as cometary, but for orbit determination, the crucial information lies in its precise position relative to known stars. To obtain that position, observers use star catalogues that list the coordinates of reference stars across the sky. In the past, this work involved visual estimates and micrometers, with an observer carefully noting the comet's offset from nearby stars in right ascension and declination. Later photographic plates allowed the entire field to be preserved. On a plate, stars and the comet appear as small images or trails, and measuring engines can determine their relative positions to high precision. In modern practice, electronic detectors and digital processing measure pixel coordinates directly and transform them into sky coordinates using reference stars whose positions are known from high-accuracy catalogues. In each case, the result is the same kind of record for a given date and time. The comet has a measured right ascension and declination on the celestial sphere. The time associated with each position is as important as the position itself. Astronomers use standard timescales and record exposure midpoints, carefully correcting for local time zones, and if necessary for light travel time effects between Earth and the comet. These timestamps ensure that each measured position can be related to the comet's motion under gravitational forces. Even small errors in timing can introduce noticeable deviations in the inferred motion when the comet is moving quickly near perihelion. For long-period comets that are observed over only a few weeks or months, the cadence and accuracy of these observational times directly influence how well the path can be reconstructed. As multiple observations accumulate over successive nights, the comet's apparent motion against the background stars becomes clear. Near the outer planetary region, the change in position from one night to the next may be modest, a shift of a small fraction of a degree across the sky. Closer in when the comet is near perihelion, and moving faster along its orbit, the nightly shift can be much larger. Astronomers compare each new position with previous ones, and with predictions from preliminary orbit fits. Any noticeable deviations prompt checks on measurement accuracy and possible refinement of the preliminary orbital elements. Even when the motion appears smooth and predictable, additional measurements reduce random errors and help average out atmospheric and instrumental effects. The brightness of the comet is also noted usually as a total magnitude that encompasses the coma and if visible part of the tail. These estimates are less precise than positional measurements, especially when the comet's light is spread over an extended area. Still, trends in brightness as a function of heliocentric distance and time provide information on how the activity responds to changing solar flux. Some comets brighten faster than a simple symmetric model would predict, others more slowly. For the object that will be recognized as the phantom comet, such brightness data contribute context, but do not alter the fact that the measured positional arc is limited in length. The number of nights on which it is observed remains small compared with the total time it spends near the Sun. In many apparitions, the comet is observed from multiple observatories at different locations on Earth. This diversity in observing sites helps reduce systematic errors that might arise from local conditions, such as atmospheric refraction near the horizon, or slight misalignments in particular instruments. Observations from different longitudes also help fill gaps due to daylight or weather at a single site. When reports from several observatories are combined, they provide a denser and more robust series of positions. For a comet with a short observational window, such coordination improves the chances that its motion can be well constrained within that window. For the phantom comet, the record consists of a set of such measured positions, drawn from the facilities active at the time of its passage. Every measured position carries an associated uncertainty. Factors such as atmospheric seeing detector noise, plate scale calibration, and the accuracy of reference star positions contribute to these error estimates. In older observations, uncertainties may be larger due to less precise catalogues and measuring techniques. Modern reductions sometimes revisit historical data, remeasuring plates, or reprocessing digital images with improved reference star catalogues to reduce systematic errors. In the case of long-period comets, observed only once, even modest improvements in individual positional accuracies can affect how well their orbits can be reconstructed. For the phantom comet, the achievable precision is bounded by the quality of the original data and by the extent to which those data can be reanalyzed. The observational arc for a comet is limited not only by its intrinsic visibility, but also by its geometry relative to the Sun and Earth. At some points in the orbit, the comet may be too close to the Sun's apparent position in the sky to be observed safely or effectively. It may set soon after sunset or rise shortly before dawn, restricting observing time to short intervals of twilight. Its path may carry it into regions of the sky where local weather patterns or seasonal daylight at observatory sites further limit observations. As a result, even though the comet remains physically active and present the number of nights on which it is measured may be relatively small. This practical constraint helps define the length of the observational arc used later for orbital solutions, once the comet fades beyond the reach of available instruments, either because it has receded from the Sun and Earth, or because its geometry renders it inaccessible. New positional measurements cease. The set of recorded positions and times is complete as far as the apparition is concerned. These data are then compiled and forwarded to central repositories where they are combined, checked for consistency, and used as the input for orbit determination. The phantom comet's measured path is represented in such compilations as a sequence of entries, each one listing an observatory code, a date and time, and the corresponding coordinates. The physical object has already moved on along its trajectory, but for analysis it is now present as a discrete data set in catalogues. There is a scientific recognition that the completeness and quality of such observational arcs vary widely between comets. Some receive dense coverage over many weeks with high precision. Others, particularly those that are faint or poorly placed, are observed only a handful of times. In the case of the phantom comet, the positions that define its visible passage form a short segment of its orbit sampled over a limited period when it was bright enough and well placed enough to be seen. Those measurements are adequate to confirm its reality as a moving cometary object and to provide a first estimate of its orbit, but they do not capture more than a small fraction of its full circuit around the Sun. Within the outer to inner progression of the narrative, this stage marks the point where the comet's existence is documented in a form that can be used quantitatively. The nucleus, coma, and tails are no longer only physical structures in space. They are also represented by sequences of coordinates and times in observational logs. The phantom comet's presence in the inner solar system during this one recorded passage is now anchored to the framework of celestial reference systems and timekeeping. Later sections will consider how this limited set of measurements is used to derive orbital elements and why in this case the resulting solutions remain too uncertain to guarantee a future recovery. Once observations of the comet have been collected and assembled into a single list of times and sky positions, the task turns from measurement to calculation. The comet's changing right ascension and declination across the sky encode how it moves in three-dimensional space under the Sun's gravity. To extract that motion, astronomers use the framework of celestial mechanics, which describes how bodies travel along conic sections, ellipses, parabolas, or hyperbolas, when the dominant force is a central gravitational attraction. For each observed time, there is a line of sight from Earth through the comet, and the goal is to find a single path that passes through all of these lines at the correct instance. This process is known as orbit determination, and it begins with a limited arc of positions recorded during the apparition. The first step is often a preliminary orbit derived from only a few well-spaced observations. A classical approach uses 3 positions each at a different time to estimate the key orbital elements: the semi-major axis, or an equivalent parameter that describes the orbit's size, the eccentricity that sets its shape, the inclination and orientation in space, and the time and distance of closest approach to the Sun. For long-period comets seen near perihelion, where their paths are nearly straight lines in the sky over short times, this preliminary solution is often taken to be parabolic with eccentricity set to 1. This assumption simplifies the first calculations by reducing the number of free parameters. Once this initial orbit is obtained, it serves as a starting point for more refined fits that allow the eccentricity to differ slightly from 1, and that incorporate additional observations. Each observation contributes information about which orbits are compatible with reality. For a fixed set of orbital elements, one can calculate where the comet would appear in the sky at any specified time. Comparing these predicted positions with the measured ones reveals residuals, the small differences between observation and model. The aim is to adjust the orbital elements so that these residuals are minimized in a least squares sense, taking into account the estimated uncertainties in each observation. When the observational arc is long, and the data points are numerous, this procedure converges to a well-constrained orbit, with small residuals and small formal uncertainties in the elements. When the arc is short and the number of measurements limited, many different sets of elements can produce residuals that are similarly small. In that case, the orbit solution is said to be poorly determined. For the comet that will be known as the Phantom, the observational arc covers only a modest span of time around its perihelion passage. The positions constrain the plane in which the comet moves and the general direction of its motion, but they do not sample enough of the orbit to distinguish cleanly between an elongated ellipse and a slightly hyperbolic curve. The solution that fits the data may be close to parabolic with an eccentricity very near 1, but the formal error bars on that eccentricity are large. Within those error bars, values slightly less than 1 and slightly greater than 1 remain compatible with the same measurements. The difference between these cases in terms of orbital energy and long-term behavior is substantial, but the difference in predicted positions over the short observed arc is small. The limited time span also affects how well the semi-major axis and period can be constrained. For a near-parabolic orbit, small changes in assumed semi-major axis produce only minor shifts in the path near perihelion. Those shifts can often be absorbed within the measurement uncertainties. As a result, the formal period that emerges from a fit can span a wide range from many hundreds of thousands of years for a bound orbit to an effectively infinite period for an unbound hyperbolic one. The orbit can still be described in terms of the direction of the incoming and outgoing asymptotes and the perihelion distance, but the global scale of the path remains poorly known. For the Phantom comet, the derived semi-major axis and period carry large uncertainties reflecting this limitation. The motion of Earth during the apparition adds both complication and information. As Earth orbits the Sun, the line of sight to the comet changes not only because the comet moves, but also because the observer's position shifts. This parallax effect helps break some degeneracies in the orbit solution, especially if observations span a significant portion of Earth's orbit. If measurements of the Phantom comet had been obtained over many months, the changing vantage point could have tightened constraints on its path. In practice, the available observations cover a shorter interval, so the leverage provided by Earth's motion is limited. The computed orbit still benefits from the fact that Earth does not remain fixed, but the full potential of parallax is not realized. Another source of uncertainty lies in the possible non-gravitational forces acting on the comet. As gas jets escape from the nucleus, they can impart small thrusts that modify its motion slightly from that predicted by pure two-body gravity. These effects are often parameterized by adding empirical acceleration terms to the equations of motion linked to the level of activity as a function of heliocentric distance. For short-period comets observed over many returns, such terms can be fitted and included in refined orbital elements. For a comet observed over a single short arc, there is usually insufficient data to separate non-gravitational accelerations from measurement noise and from uncertainties in the gravitational parameters. In the case of the Phantom comet, fitting non-gravitational terms would likely overinterpret the limited data, so the standard orbit solutions either neglect them or include them only in a basic way, adding further uncertainty to any long-term extrapolation. Measurement errors play a role at each stage of this process. Each recorded position has an associated error ellipse in the sky, reflecting the finite precision of the instruments and reference catalogues. When these errors are propagated through the orbit fitting procedure, they translate into uncertainties in the orbital elements. For comets with rich data sets, the effect of a single measurement error is diluted by the presence of many other measurements. For a comet with only a small number of positions, a few points with larger than expected errors can skew the solution more strongly. Attempts to mitigate this effect include weighting observations according to estimated quality and sometimes discarding outliers that disagree systematically with the fitted orbit. For the Phantom comet, the final adopted orbit reflects such considerations, but the small sample size leaves residual sensitivity to individual measurements. Once an orbital solution is obtained, it is usually expressed in a standard form with elements such as inclination, longitude of ascending node, argument of perihelion, perihelion distance, and an energy-related parameter that may be a semi-major axis or an equivalent. Ephemerides can then be generated tables listing predicted positions of the comet at future dates. These predictions are used to plan further observations and for periodic comets to forecast their returns. In the case of a long-period comet with an uncertain orbit, the ephemerides are accompanied by warnings that predicted positions may carry large errors. For the phantom comet, ephemerides beyond the observed interval extend a path that fits the data, but that may diverge significantly from the true trajectory as time passes. There is a recognized scientific understanding that orbit determination from short arcs can produce formally precise elements that are not physically reliable when extrapolated far in time. The numerical fitting process can yield small residuals and small internal errors for the data at hand, yet the family of orbits that fit within observational uncertainties may still be broad. In such cases, the quoted elements should be interpreted as a representative solution, rather than as a definitive description of the comet's path. For the phantom comet, this situation applies the orbit in catalogues summarizes what is known, while the range of what is possible remains wide. Within the outer to inner structure of the narrative, this section focuses on the transition from direct observation to mathematical description. The comet's passage through the inner solar system is now represented not only by light in telescopes, but by a set of orbital elements derived from its limited observational arc. The physical body continues along its path, but in human records it becomes a trajectory encoded in numbers, with uncertainties that reflect the brevity and precision of the measurements. Later evolution of the story will proceed with these elements as the starting point, considering what can and cannot be said about the comet's future based on this constrained description. Near perihelion, the comet reaches the smallest distance between its nucleus and the Sun, and the conditions at its surface change more rapidly than at any other point along its orbit. The sunlight now arriving at the nucleus is many times stronger than it was in the outer regions because the solar flux increases with the inverse square of distance. The outer layers of the nucleus warm to temperatures at which water ice and several other volatile species sublimate vigorously wherever they are exposed or can be reached by heat through fractures and pores. Gas production rises to its peak, and the coma becomes dense and extensive compared with earlier stages. At the same time, the structural integrity of the nucleus is tested by thermal stresses, gas pressure in subsurface cavities, and rotational torques induced by asymmetric outgassing. The same processes that make the comet most visible also place the greatest strain on its internal structure. The surface energy balance at perihelion is dominated by absorption of sunlight thermal radiation and sublimation. On the day side, the dark low albedo surface absorbs a large fraction of incoming light, raising local temperatures. Some of this energy radiates away as infrared emission. Some goes into driving phase changes in the ices. If freshwater ice is exposed, the sublimation rate can become high enough that a dense gas layer forms just above the surface, especially in topographic depressions or pits, where gas can accumulate briefly before escaping. In these regions, the local gas pressure can rise above the very low background of the coma, exerting mechanical forces on surrounding material. If overlying layers are weak or fractured, these pressures can open new vents or widen existing cracks, altering the geometry of outgassing over short timescales. Thermal gradients also develop between the day side and night side, and between surface and subsurface layers. The surface heats and cools over each rotation, while deeper layers respond more slowly, producing a vertical temperature profile that changes with depth. Differences in thermal expansion between materials and between regions, with different illumination histories, lead to stresses within the near-surface crust. Over many rotations across the perihelion passage, these stresses can propagate and accumulate. When combined with pre-existing fractures produced during earlier orbital evolution, they contribute to the initiation and growth of cracks. Some cracks may remain shallow, merely rearranging the outermost dust and ice. Others may connect to deeper voids, providing new pathways for gas and heat. The internal composition and porosity of the nucleus play a key role in how it responds to these conditions. If the interior is highly porous with many interconnected voids, gas produced by sublimation can percolate through the structure and escape, gradually reducing the likelihood of large pressure buildups. If instead the interior contains isolated pockets of volatile rich material, sealed beneath more consolidated layers, gas produced in these pockets can accumulate until local pressure exceeds the strength of the surrounding material. In that case, a sudden release can occur when a weak point fails, ejecting chunks of the overlying crust and dust into the coma. Observations of several comets near perihelion show discrete outbursts, consistent with such pressure-driven events, although the exact configurations inside each nucleus remain uncertain. Rotation continues to modulate these effects. As the nucleus spins, different regions pass through prolonged exposure to sunlight or extended periods in shadow. If the spin axis is oriented so that one hemisphere receives more intense heating over the perihelion segment of the orbit, that hemisphere may experience more rapid erosion, stronger gas flow, or greater fracturing. Asymmetric erosion in turn can shift the distribution of mass within the nucleus, altering its moment of inertia and potentially changing its rotation rate or axis orientation. Gas jets that rise from particular locations can apply torques as they flow, gradually spinning the nucleus up or down. In some comets, measurements show changes in rotation period across perihelion consistent with such torques. For the Phantom comet, no direct rotational measurements exist, but the same physics applies near perihelion. The coupling between outgassing and rotation reaches its strongest values. In the most extreme cases, these combined stresses can lead to fragmentation of the nucleus. When internal cohesion and gravity are no longer sufficient to counteract the forces from gas pressure, thermal stress and rotational acceleration, the body can break into two or more major pieces. The fragments separate, each carrying a portion of the original mass, and may continue along similar or slightly diverging orbits. Observations of some long-period and short-period comets have recorded such breakups, with the coma elongating and multiple condensations appearing. Smaller fragments may disintegrate further, releasing dust that rapidly merges into the surrounding coma and tail. Whether the Phantom comet remains intact through its perihelion passage or suffers partial fragmentation is not known, because the observational record does not include detailed monitoring of its inner structure or brightness variations at the necessary cadence. In addition to macroscopic fragmentation, steady erosion of the surface at perihelion reshapes the outer layers of the nucleus. Regions where sublimation is strongest retreat more quickly, leaving behind depressions, scarps, and irregular slopes. The thickness of material removed during a single passage depends on the gas production rate, the duration of intense activity, and the density of the nucleus. For some comets, estimates indicate that several meters of surface can be lost over one perihelion passage in highly active areas, while more sheltered regions lose far less. Over many such passages, this process can significantly reduce the size of a nucleus or alter its shape. For a long-period comet that may only pass close to the Sun, a small number of times the cumulative effect over its entire history can still be substantial. The energy input near perihelion also affects subsurface layers. Heat penetrates deeper than in earlier stages, especially beneath areas of high activity, where the insulating dust layer is thin or removed. Sublimation fronts retreat inward as volatile rich layers are depleted. Some of the gas released at depth migrates to the surface, while some may refreeze in cooler regions, redistributing volatiles within the nucleus. Over the perihelion passage, a complex pattern of sublimation and recondensation develops, modifying porosity and composition at different depths. The details of these transformations depend on initial structure and composition, both of which are uncertain for any given comet, including the Phantom one. Another outcome of intense perihelion heating is the alteration of the dust layer that remains after volatiles are removed. As ices beneath the surface sublimate, the overlying dust grains settle and compact, forming a more cohesive crust in some areas. In others, mechanical disturbances from gas escape or small collapses may loosen material, creating local accumulations of unconsolidated dust. The overall mechanical properties of the surface can thus change over the course of the perihelion passage, influencing how the nucleus will respond during any future close approach, should it remain bound and return. The coma and tails at perihelion reflect these near-surface processes. Strong gas production supports a bright extensive coma, with dense inner regions and complex jet structures. Dust carried away forms a long tail, while ions continue to stream along magnetic field-guided paths. Variations in outgassing drive temporal changes in brightness and structure, some of which can be observed from Earth when conditions allow. For the Phantom Comet, the available observations capture only a limited portion of this behaviour, but the physical processes underlying its perihelion activity are consistent with those seen in other long-period comets. Within the outer to inner path, this region corresponds to the deepest immersion in the Sun's radiative and gravitational influence. Thermal, mechanical and dynamical stresses on the nucleus reach their maximum. Material is removed at the fastest rate. Internal structures are most affected, and the observable signatures of activity are most pronounced. Once the comet moves past perihelion and begins to recede, the solar flux will decrease, gas production will fall, and the nucleus will cool. At that later stage, the consequences of the perihelion passage, any reshaping of the surface, any changes in rotation state, and any fragmentation will guide the subsequent evolution of both the solid body and the surrounding dust and gas. After perihelion, the comet moves away from the Sun, along the second half of its elongated orbit. The heliocentric distance increases, and with it the solar flux at the nucleus decreases according to the same inverse square dependence that intensified heating on the way in. The surface that near perihelion supported vigorous sublimation now receives progressively less energy per unit area. Temperatures in the upper layers begin to fall first on the night side, and in regions that rotate into shadow, then more generally as the entire orbit carries the nucleus outward. Gas production, which reached its maximum around closest approach, declines as the vapor pressure of water ice and other volatiles drops. The coma, once dense and extensive, gradually thins. Near the nucleus, the density of gas falls, the collisional region shrinks, and the transition to free molecular flow moves closer to the surface. The retreat of activity does not occur everywhere at the same rate. Areas that were strongly heated at perihelion, where insulating dust mantles were thin or removed, may continue to release gas for some time, as residual heat diffuses inward and sustains sublimation beneath the surface. Regions that remained more insulated cool more quickly and fall quiet earlier. The rotation of the nucleus continues to modulate local conditions, carrying surfaces that were recently illuminated into darkness and returning shadowed zones into sunlight, but the overall trend is downward in temperature and gas flux. The daily temperature range narrows as the energy input decreases. Subsurface layers that were warmed during perihelion now release stored heat slowly toward both the surface and interior smoothing gradients that were sharpest near closest approach. As gas production declines, the inner coma responds. The density of molecules near the nucleus drops, reducing the frequency of collisions. The radius of the collisional regime contracts, and a larger fraction of the space around the comet becomes dominated by free molecular flow, where particles move largely without colliding until they leave the vicinity entirely. The brightness of the coma falls as fewer gas molecules and dust grains are present to scatter sunlight. Structures that were once prominent, such as jets and fans, fade or disappear as their source regions lose the ability to drive strong flows. Where gas still escapes, it does so in weaker streams, producing less pronounced anisotropies. Observationally, the central condensation diminishes, and the extent of the visible coma shrinks, eventually returning toward a state where the nucleus appears again as a nearly stellar point surrounded by only a small diffuse halo. Dust behavior adjusts to the new conditions. Near perihelion, strong gas drag lifted and accelerated grains of various sizes away from the nucleus, feeding a broad dust tail and a trail along the orbit. As the gas flux weakens, the capacity of the flow to entrain new grains diminishes. The smallest particles, which require only modest forces to detach, may continue to be lifted from the surface for a time, but larger aggregates remain increasingly bound. The total number of new grains added to the coma and tail decreases. Dust already released continues its motion under gravity and radiation pressure. The tail can remain extended and visible for some time, even as the source weakens, because particles that have already been ejected do not immediately disappear. While the comet recedes, the geometry between Sun nucleus and observer changes, altering the apparent length and orientation of the tail, but physically the dominant trend is a slow thinning, as older dust spreads out and new input falls. The ion tail responds more quickly to the fall in gas production. Ion formation depends on the availability of neutral molecules in the coma. As neutral densities drop, fewer ions are created per unit time, and the mass loading of the solar wind decreases. The region of strong interaction between solar wind and cometary plasma contracts. The bow shock or bow wave weakens, and any diamagnetic cavity that formed near the nucleus shrinks or disappears. The draped magnetic field and associated cometary plasma still form a tail that extends downstream, but its density falls, and its visibility in emission lines and bands declines. Because the plasma responds on timescales comparable to ionization and flow times, these changes can occur more rapidly than the more gradual fading of the dust tail. Inside the nucleus, the thermal wave from perihelion continues to propagate. Heat deposited in the near-surface layers at closest approach moves inward over time through conduction, and in some regions through gas diffusion in pores. This inward transport can continue for a while even as the surface cools. At certain depths, temperatures may reach maxima after perihelion, rather than exactly at it, depending on the thermal properties and rotation. In those layers, any remaining volatile ices can sublimate and migrate along pores and fractures, potentially refreezing in cooler regions or feeding slow delayed gas flow toward the surface. In this way, the internal structure of the nucleus continues to evolve as the comet recedes with sublimation, fronts retreating and volatile distributions adjusting, even when the outer appearance shows declining activity. The mechanical consequences of perihelion passage also persist. Fractures opened by thermal stress and gas pressure remain as pathways for future gas and heat flow, even when activity is low. Areas where surface material collapsed or was removed now present new topography depressions, cliffs and irregular slopes that can influence illumination patterns on any future return should the orbit be bound. Changes in rotation state induced by asymmetric outgassing, such as slight shifts in period or axis orientation, remain encoded in the nucleus's spin. For a long period comet with a very extended orbital period, these modifications may have little practical consequence until far in the future. For the phantom comet, whose long-term trajectory is uncertain, they nonetheless represent changes in internal and external conditions set during this one intense passage. From a dynamical standpoint, the non-gravitational forces that were strongest near perihelion weaken as gas production falls. The small accelerations produced by jets and asymmetric outgassing diminish, and the comet's motion becomes increasingly dominated again by gravity alone. Any cumulative shifts in the orbit that occurred during the high activity phase have already been applied. Further changes from this source become negligible. Gravitational perturbations from planets along the outbound leg remain possible, especially if the comet's geometry brings it near one of the giant planets, but their magnitude depends on specific timing and distances. For the phantom comet, the short observational arc around perihelion does not fully constrain whether such encounters occurred on the outbound leg, leaving this aspect of its evolution only partially known. As the heliocentric distance increases further, the comet enters a regime where water ice sublimation becomes inefficient. The vapor pressure of water falls sharply with temperature, and beyond certain distances the energy input is insufficient to sustain any significant water-driven gas flow. More volatile species, if still present near the surface, may continue to sublimate at low rates, but their contributions are small. Surface temperatures approach values where activity is again dominated, if at all, by the most volatile components, similar to the early activation phase on the inbound leg. The the comet's appearance in telescopes shifts back toward that of a small faint fuzzy patch, then toward near invisibility as brightness declines below detection thresholds. Eventually at distances comparable to those where it first became measurable, it passes beyond the reach of the instruments that recorded its arrival. There remains an uncertainty in the exact distances and times at which these transitions occur for any specific long-period comet, including this one. The detailed composition, porosity, and topography determine how long noticeable activity persists as the comet recedes. Some comets exhibit asymmetric light curves fading more slowly after perihelion than they brightened before it, while others decline more rapidly. In the absence of continuous monitoring, the precise shape of the phantom comet's light curve on the outbound leg is not known. Still, the governing principle is clear. Decreasing solar flux leads to decreasing sublimation, thinning the coma, and shortening the active phase until the nucleus returns to a largely inert state. In the outer to inner and then back outward sequence, this stage corresponds to the comet's gradual disengagement from the region of strong solar influence. The nucleus is no longer at maximum stress, gas and dust production are in decline, plasma interactions weaken, and the visible structures that marked its perihelion passage soften and shrink. The physical object, however, continues along its orbit, carrying with it the modifications imposed during its time near the Sun. Material lost as gas and dust now resides in the surrounding space as part of dust trails, meteoroid streams, and diffuse plasma that follow related paths. The comet itself moves toward distances where the thermal and dynamical conditions will again resemble those of the distant reservoir from which it came, while the record of its brief bright phase remains in both the altered nucleus and the limited set of observations made during its passage. Long after the nucleus has passed perihelion and faded from view, the material it released remains distributed through the inner and intermediate regions of the solar system. Dust grains and larger meteoroids that left the surface under gas drag now occupy orbits that are similar but not identical to that of the parent comet. At first, many of these particles form a relatively narrow swarm close to the comet's path, trailing slightly behind or leading slightly ahead depending on the details of their ejection and the influence of radiation pressure. Over time, small differences in orbital period inclination and eccentricity cause this swarm to stretch into an elongated stream. The particles become spaced out along the orbit, forming what is known as a meteoroid stream, a band of solid material that follows the general path the comet once traced, even when the nucleus itself is no longer visible, or in some cases no longer intact. The dynamics of this stream are set by the same gravitational field that governs the planets, and the parent comet modified by the additional contributions of radiation pressure, and for very small grains pointing Robertson drag. Particles that are large enough for gravity to dominate retain orbits that differ only slightly from the comet's, maintaining similar semi-major axis eccentricities and inclinations. They remain close to the original path, forming a relatively thin ribbon of matter in space. Smaller grains with lower masses and larger surface area to mass ratios experience stronger radiative effects. Their orbits can evolve more rapidly, shifting inward in semi-major axis and gradually spiraling toward the Sun. The stream thus develops a size-dependent structure with larger meteoroids concentrated near the original orbit, and smaller dust grains more widely dispersed. As the stream ages, planetary perturbations become increasingly important. Each time a meteoroid passes near a planet, its path can be deflected slightly. Over many revolutions, these small changes accumulate, altering the inclination or nodal longitudes of the particles. Resonances with planetary orbital periods can trap some meteoroids into configurations where specific aspects of their orbits repeat on long timescales, while others are moved away from resonant conditions and dispersed. The overall effect is a gradual broadening of the stream both along and across the original path. In some regions, gravitational effects can concentrate material, forming denser filaments. In others, they can thin the distribution. For the phantom comet, any meteoroid stream produced by its passage would evolve under these same influences, even though its specific structure remains unobserved. The initial mass and ejection history of the stream influence how detectable it becomes. If the comet shed a large quantity of material over a range of sizes, the resulting stream may develop sufficient column density that when intersected by a planet's orbit it produces an observable meteor shower. If the mass loss was modest or concentrated in sizes that are quickly removed by radiative forces, the stream may remain too sparse to create a noticeable enhancement in meteor rates. For the Phantom Comet, the total mass released as meteoroids during its single observed passage is not directly measured. Its brightness and gas production provide indirect constraints, but the efficiency with which dust and larger fragments were ejected and their size distribution are not known. As a result, whether its stream, if it exists, contributes significantly to meteor activity at any planet remains uncertain. When a planet's orbit intersects a meteoroid stream, particles that enter its atmosphere produce meteors. Each meteoroid encounters atmospheric gas at high relative speed, compressing and heating the air along its path, and causing both the atmospheric molecules and the particle itself to emit light. The visible trail persists only for fractions of a second to a few seconds, depending on particle size, speed, and composition. For an observer on the planet's surface, a meteor shower occurs when the planet passes through a region where the density of meteoroids is higher than that of the general sporadic background. The apparent radiant point in the sky from which the meteors seem to originate corresponds to the direction of the stream's velocity vector relative to the planet. The orbit of the stream can be reconstructed from observations of individual meteors. By measuring the direction and speed of meteor trails with photographic video or radar methods, scientists derive the pre-atmospheric orbits of the meteoroids. When many meteors share similar orbital elements, they are grouped into a single stream. These elements can then be compared with the orbits of known comets and asteroids. When a close match is found in inclination, eccentricity, and perihelion distance, a parent body is identified. For several well-studied streams, such matches are strong, linking specific comets to recurring meteor showers. In other cases, streams have been identified without a clear parent or with multiple candidate parents. The Phantom Comet, with its uncertain orbit and single observed apparition, could in principle be associated with a stream whose orbit lies within the range of its possible paths, but the uncertainty in both the comet's orbital elements and any stream's evolution makes such an association difficult to demonstrate. Over long timescales, Poynting-Robertson drag acts as a slow but persistent brake on small dust particles in the stream. As these grains absorb sunlight and re-radiate the energy at longer wavelengths, they lose a tiny amount of orbital energy and angular momentum. This causes their orbits to shrink, gradually bringing them closer to the Sun. The process operates over timescales of hundreds of thousands to millions of years for millimeter scale grains at typical inner solar system distances. As dust spirals inward, it leaves the original narrow stream and becomes part of the broader population of interplanetary dust, contributing to the diffuse background known as the zodiacal cloud. In this way, material from the Phantom Comet, if ejected in the form of small grains, could eventually become part of this general dust population, losing any clear dynamical link to its origin. Larger meteoroids experience Poynting-Robertson drag much less strongly, and can remain in stream-like orbits for much longer. However, they are still subject to collisions with other particles. Over time, collisions can fragment larger bodies into smaller pieces which then evolve more rapidly under radiative forces. The balance between collisional fragmentation and radiative removal sets the effective lifetime of different size classes within the stream. Estimating these lifetimes for a specific stream requires knowledge of the particle size distribution and ambient dust densities, both of which are not well constrained for most cases. For the Phantom Comet's potential stream, these details remain model-dependent. There is an additional uncertainty surrounding the exact number of meteoroid streams present in the inner solar system and their parentage. Observational surveys detect many showers, some strong and recurring, others weak and sporadic. For some showers, associated streams are clearly defined. For others, only a diffuse enhancement in meteor rates suggests a coherent origin. Some streams line up well with known comets, others do not. it is likely that some streams originate from comets that have since disintegrated, or that were only poorly observed, and that their names and orbital elements have faded from human catalogues, while their debris continues to intersect planetary orbits. In this context, the phantom comet's possible contribution to present-day meteoroid populations fits naturally into a pattern where many streams have incomplete or uncertain links to specific parent bodies. From a broader perspective, the cumulative effect of many comets, including one-time visitors, is to maintain a steady supply of dust and small meteoroids in the inner solar system. Each perihelion passage removes material from a nucleus and injects it into heliocentric orbits that eventually lead to incorporation into the zodiacal cloud, into meteoroid streams, or into the atmospheres and surfaces of planets and smaller bodies. Over the age of the solar system, this continuous input has built and maintained the general dust environment through which the planets move. The phantom comet contributes to this environment in proportion to the amount of material it lost during its passage, regardless of whether that contribution can be distinguished from those of other comets. Within the outer to inner sequence of the narrative, this section focuses on the stage where the comet's influence persists primarily through debris, rather than through the visible presence of the nucleus and its active coma. The physical body has already receded beyond the range of most observations, cooling and returning toward a more inert state. Its past activity is recorded in the distribution of dust and meteoroids left behind, which follow related orbits and undergo their own long-term evolution under gravity and radiation. The phantom comet's future presence in the inner solar system thus becomes indirect, expressed through streams and clouds of particles that occasionally interact with planets, and that gradually merge into the broader background of interplanetary dust long after the nucleus itself has passed beyond the reach of direct measurement. Far from the inner planets, the comet's nucleus continues outward along its orbit while its visibility declines. The distance from the Sun grows steadily, and with it the solar flux decreases to levels that no longer sustain substantial gas production. The last traces of a detectable coma vanish, leaving the nucleus as a small dark body with only minimal or no ongoing activity. Its motion is now governed almost entirely by gravity, with non-gravitational forces from outgassing reduced to negligible levels. The orbit that describes this motion has already been fitted to the available observations, but the limited length of the observed arc means that the fitted elements do not uniquely determine the comet's long-term trajectory. The physical body follows a single path, yet within the range of orbital solutions allowed by the data, more than one long-term outcome remains compatible with what was seen during its brief appearance. In the framework of two-body motion under the Sun's gravity, each orbit can be classified by its total specific energy. If that energy is negative, the orbit is bound and elliptic. If it is zero, the orbit is parabolic. If it is positive, the orbit is hyperbolic and unbound. For comets observed near perihelion with very elongated paths derived, orbits often have eccentricities close to 1 and energies close to 0. Small changes in the fitted parameters within their uncertainties can move the solution from slightly bound to slightly unbound, or the reverse. Over the short span of the observations, such changes do not produce large differences in predicted positions, so they remain consistent with the same data. Over long timescales, however, the consequences differ. A bound orbit will eventually bring the nucleus back toward the inner regions after a period that can span hundreds of thousands or millions of years. An unbound orbit will carry it away from the solar system on a one-way path. For the comet in question, computed orbit solutions place it among long-period objects with very high eccentricity and a perihelion distance that brings it into the inner solar system only briefly. The formal uncertainties on its energy-related parameters are large enough that both very long-period bound solutions and marginally hyperbolic solutions fall within the allowed range. In practice, this means that the measurements do not decisively distinguish whether the nucleus remains a distant member of the solar system or becomes an interstellar object after its passage through the planetary region. Its present location along its path at any given time is specific, but its future classification as bound or unbound remains an open question in the absence of additional data. Beyond the region where the giant planets orbit, planetary perturbations become infrequent and weak, but the outbound leg of the comet's path can still be influenced by encounters that occurred earlier. A close approach to a massive planet during either the inbound or outbound trajectory can change the comet's velocity vector, enough to alter its overall orbital energy. Numerical integrations of comet orbits often show that interactions with Jupiter and Saturn play a major role in determining whether a long-period comet remains bound or gains sufficient energy to escape. For the Phantom Comet, the uncertainties in its elements propagate into uncertainties in any reconstructed encounter history, so different realizations of its orbit within the observational error bounds can lead to different conclusions about past and future planetary interactions. As the comet moves to greater heliocentric distances, other gravitational influences also become relevant on very long timescales. The solar gravitational field weakens with distance, while the gravitational potential of the Milky Way galaxy and of passing stars becomes relatively more important. For a comet that remains bound on a highly elongated orbit, these galactic and stellar perturbations can once again modify its path, much as they did when it resided in the distant reservoir before this inward excursion. The aphelion of its new orbit may lie at distances where the galactic tide and stellar passages reshape its parameters over millions of years, potentially altering its perihelion distance and orientation before a future return. For a comet that escapes onto a hyperbolic trajectory, similar galactic influences act, but now, on a body that is no longer gravitationally bound to the Sun, and that gradually merges into the general population of small objects in the local galactic environment. From the standpoint of orbit catalogues, the comet is effectively a lost object when its predicted positions based on the fitted orbit become too uncertain to support future recovery. Ephemerides extend the solution forward in time, providing expected sky coordinates at given dates, but for an orbit derived from a short arc, the region of the sky in which the comet might actually be located grows larger as time passes, because small differences in the initial conditions lead to divergences in position along the path. Searches for a faint returning nucleus would need to cover this broad region with sensitive instruments. If repeated searches at expected returns reveal no object, and if the predicted uncertainties make the search region too large to survey effectively, the comet remains classified operationally as lost. For a long-period comet whose next possible perihelion would occur far in the future, the practical outcome is similar even if the orbit is technically bound. Non-gravitational forces that were strongest near perihelion leave only small residual imprints on the outbound trajectory. The integrated effect of asymmetric outgassing during the active phase may have shifted the orbit's energy and angular momentum slightly, but once activity ceases, these changes are fixed. Because the activity-driven accelerations are not well measured for a comet, with a short observational arc, the magnitude and direction of these shifts remain uncertain. As a result, the true post-perihelion orbit can differ from the purely gravitational fit by amounts that become significant when projected over long times. This source of uncertainty adds to that from measurement errors and limited time coverage, further widening the range of possible future paths consistent with the data. In theoretical treatments of comet populations, objects like this are represented statistically rather than individually. Models of the Oort cloud and of comet injection into the inner solar system use distributions of initial orbits and incorporate gravitational interactions with planets, the galactic tide, and passing stars. They track how many comets are expected to return on bound orbits, how many are ejected, and how many are perturbed into new long-period paths. Within such models, a comet with parameters similar to those of the phantom object has a probability of remaining bound and a complementary probability of escape values that depend on assumptions about the initial population and encounter frequencies. From the perspective of the outer regions of the solar system, the end state for the nucleus is either a distant, slowly moving member of a bound cloud or an object on an outward path into interstellar space. In the bound case, the nucleus spends almost all of its time far from the Sun, moving slowly near aphelion, with only brief returns to the inner region separated by very long periods. In the unbound case, it continues outward, crosses the boundaries of the heliosphere, and enters a regime where the Sun's gravitational and plasma influence gradually give way to the conditions of the local interstellar medium. In neither case does it retain any significant coma or tail once it has receded beyond the distances where solar heating can sustain sublimation. Within the outer to inner and back outward progression, this section describes the region where the comet's physical visibility has ended, but its long-term dynamical status is still set by the combination of earlier gravitational and non-gravitational influences. The nucleus moves on a path that is well described by the laws of celestial mechanics, but only partly constrained by the limited observations available. Whether it remains loosely bound to the Sun, or ultimately joins the interstellar population, its motion continues under the combined gravitational fields of the Sun and the galaxy, while its recorded passage through the inner solar system persists in orbit catalogues as a set of elements with significant uncertainties identifying it in practice as a lost comet, whose precise future track cannot be fully reconstructed from the data obtained during its single observed apparition. In the years following its passage through the inner solar system, the comet's presence is maintained in two distinct domains: the physical path of the nucleus in space, and the representation of that path in observational records and orbital catalogues. In space, the nucleus recedes into regions where direct observation becomes increasingly difficult, then impractical and eventually impossible with the instruments that recorded its apparition. In the records, the comet remains as a set of measured positions, magnitudes, and a derived orbit stored in databases and printed circulars. These two descriptions, physical and mathematical, refer to the same body, but only the second remains readily accessible once the nucleus itself has faded beyond detection. For a comet observed only once, this mathematical description becomes the primary means by which its existence is known and its potential future presence is considered. The observational archive contains the original measurements, times, right ascensions, declinations, and brightness estimates from multiple observatories. These data are preserved not only in their initial form, but often in revised reductions that take advantage of improved reference star catalogues and calibration techniques. When new astrometric catalogues refine star positions, it becomes possible to reprocess older comet observations, reducing systematic errors in the comet's derived coordinates. Such revisions can tighten residuals in orbit fitting and slightly adjust the orbital elements. For many comets with rich data sets, this process leads to noticeably improved orbits. For the Phantom comet, with its short observational arc reprocessing, can reduce internal inconsistencies, but cannot fully overcome the limitations imposed by the brief time during which the object was observed. Orbit catalogues summarize each comet's path in a compact set of elements. For long-period objects, these elements are often given both in osculating form, appropriate to a specific epoch, and in a so-called original or barycentric form that approximates the orbit before the comet entered the planetary region. The latter elements are used to infer whether the comet likely came from the Oort cloud on a bound orbit or entered the solar system on an interstellar trajectory. Calculating these original elements requires integrating the orbit backward through the planetary system, accounting for gravitational interactions with the planets, and when possible for non-gravitational effects from outgassing. When an orbit is poorly constrained, these integrations produce a family of possible original elements, rather than a single precise value. In such cases, the comet is often assigned to a broad category, such as a new long-period comet without a firm conclusion about its detailed origin. For the Phantom comet, the published orbital solutions place it within the class of long-period comets, whose energies are close to the boundary between bound and unbound states. The associated uncertainties reflect the spread of possible orbits that remain compatible with the observations. Some realizations of the solution correspond to an object that originated in a distant bound reservoir and that will return after a very long interval. Others correspond to an object on a path that will not bring it back. In catalogues, the elements are presented with their formal errors, providing a quantitative measure of this ambiguity. The classification as a lost comet acknowledges that despite these computed orbits, no practical prospect exists for recovering the body at a future return within any planning horizon given the uncertainties involved and the faintness expected at large distances. Within population studies, comets with such uncertain orbits contribute statistically rather than individually. When researchers estimate the flux of new long-period comets into the inner solar system, they count both well-observed objects and those seen only briefly like the phantom comet. Each contributes to distributions of perihelion distances, inclinations and original energies. These distributions are compared with models of the Oort cloud and of the effects of galactic tides and stellar perturbations. In this context, the details of any single comet's orbit matter less than the aggregate pattern. The phantom comet appears as one data point among many its individual uncertainties folded into wider error bars on the overall distributions. Its contribution influences how many comets are inferred to arrive from different parts of the distant reservoir, and how many are thought to leave the solar system after their encounters with the planets. The record of the comet's physical properties during its apparition is limited. Notes on coma size, tail orientation and brightness provide only a partial snapshot of its activity. No direct measurements of nucleus size, rotation, state or composition exist. For some comets, spacecraft visits supply detailed surface images in situ plasma and dust measurements, and precise mass and density determinations. These data serve as templates for interpreting less complete observations of other comets. The phantom comet is interpreted entirely through such analogies. Its classification as a typical long-period object implies a nucleus composed of a mixture of ices and dust, with low bulk density covered by a dark processed surface layer activated by solar heating, according to general thermal and sublimation models. Any specific structural or compositional features beyond this general description remain unknown. Over time, catalogues are updated, new comets are added, orbits are refined, some entries emerged when objects are recognized as returns of previously known comets. For long-period comets with extremely long predicted periods, the original entries remain unchanged apart from occasional re-reductions of old data. The phantom comet's listing persists in this way, with its discovery date discoverers and orbital elements forming a fixed record within the evolving catalogue. It is not removed unless future analysis reveals an error that reclassifies it as some other type of object, which is unlikely given its clearly cometary appearance at discovery. Instead, it stays in the list of long-period comets, with single recorded apparitions joining a group of similar objects whose paths remain only partially constrained. The physical nucleus, meanwhile, continues its motion beyond the regions where telescopes that originally recorded it can detect it. If its orbit is bound, it spends most of its time near aphelion, moving slowly through the outer solar system, in conditions analogous to those of the reservoir from which it came. If its orbit is unbound, it travels outward through the heliosphere, and eventually into interstellar space, carrying with it material that once resided in the early solar system's formation region. In neither case does its later trajectory alter the observational fact that it was seen once, and then not again within the span of current records. The streams of dust and small meteoroids released during its passage continue their own evolution, though any link between them and their source gradually becomes more difficult to detect. Within the outer to inner and back outward progression, this final section remains focused on the most internal layer of treatment, the representation of the comet's path and properties in human records, models and catalogues. The time of active visibility is past. The period of gas and dust production has ended. The nucleus has returned to a state of slow motion in distant regions. What persists in accessible form is the finite set of measurements and derived quantities stored in archives. The phantom comet is thus present in the solar system, both as a small dark body travelling under gravity in an environment of low temperature and weak radiation, and as a small group of numbers and notes in catalogues of long-period comets, where it remains identified as an object seen once and never recovered with an orbit that aligns with the laws of celestial mechanics, but that cannot be traced with enough precision to guarantee any future observation. In the distant regions beyond the giant planets, where sunlight falls weakly and changes in position, unfolds slowly, many small bodies follow elongated paths around the Sun. Each nucleus turns on its axis, presents alternating faces to the faint light, and completes only a small number of circuits over the full age of the solar system. Ices remain stable beneath darkened surfaces. Dust mantles hold their shapes for long intervals. Internal temperatures hover only slightly above their ancient values. The space between these bodies is wide, filled mostly with the low-density gas and dust of the interplanetary and interstellar media, with occasional particles from past comets drifting along stretched orbits. Closer in, where the planets travel on nearly stable ellipses, the dust left behind by many comets and asteroids forms a faint, persistent cloud. Grains follow paths that tilt and stretch around the Sun, intersecting planetary orbits, and sometimes entering atmospheres as brief meteors. Most of the time, these particles pass unnoticed, their presence registered only in the diffuse brightness of the zodiacal light, and in the slow accumulation of impacts on airless surfaces. The trails and streams produced by individual comets gradually merge into this broader environment, losing sharp boundaries and becoming part of a continuous background that changes only slowly with time. Around one planet, instruments continue to record the sky, adding new entries to the catalogues that already hold many comets and asteroids. The positions of older objects remain written, their orbits preserved in standard forms, their discovery dates, and observing histories noted. Some of these objects return and are seen again. Others have orbital periods so long that no second apparition will occur within the span of present records. A few, such as the Phantom Comet, remain as single passages represented by short observational arcs and by orbital elements that carry wide uncertainties. Their nuclei have moved on to distant regions, while their recorded paths rest quietly in archives and databases. In this combined setting of distant nuclei, diffused dust and written records, the processes that govern comets continue in the same way, regardless of how often they are observed. Bodies form are scattered, drift inward, become active, release material, and then fade again into cold regions or into interstellar space. Dust and meteoroids maintain the inner environment. The heliosphere continues to extend outward against the interstellar medium. The galactic tide and passing stars continue to shape the outer reservoirs. The Phantom Comet occupies its place within this system as one nucleus that has completed an inward excursion and now follows its later path unseen, while its recorded apparition remains as part of the accumulated description of how small bodies move through the solar system over long timescales.